Hi everybody, we are group 5 and our paper is assessing the energy consumption and performance of web GPU and WebGL in Android devices. I'm here to briefly introduce guys with the motivation and context of this paper. The mobile application ecosystem has grown by leaps and bounds in the last decade. The smartphone has become a major tool for both leisure and business activities. More and more developers are venturing into mobile application development, where WebGPU and WebGL are their preferred graphics rendering technologies. So many people will want to know what are WebGPU and WebGL. WebGPU and WebGL enable developers to harness hardware-accelerated graphics rendering within web processors, empower the creation of rich, highly interactive applications. This technology spans across various domains, ranging from gaming to scientific research. WebGL is a JavaScript API for rendering 2D and 3D graphics in web processors. WebGPU is a more modern graphics API designed for web use, providing lower-level access to the GPU for better performance and multi-threading support. So many people think that, oh, the WebGPU is the successor to WebGL, so WebGPU may have better performance and less energy consumption. So which one is better? WebGL is a widely used technology for web-based graphics rendering, while WebGPU is an energy and more advanced technology expected to offer improved performance and capabilities for web developers. In summary, the choice between the two may depend on the specific requirements and processor support for a given project. And we aim to help developers understand the energy consumption and performance of WebGPU and WebGL in this project, in this paper. So we also want to aid them in making informed technology choices.
So in the design phase, we first make sure to decide the metrics that we need to measure. The first is energy consumption, which is the amount of energy consumed when implementing the web application. And the second is memory consumption, the amount of RAM used by the web application during the test in kilobytes. The third is delayed frame rate, the ratio of delayed frames, which represents the proportion of frames that were delayed or arrayed later than expected compared to the total number of frames. There are two benchmarks that we need to measure the battery consumption and the performance. As you can see the link in the third is web application. We tested the benchmarks in Google Chrome and in Firefox, but we finally find that the Firefox Natively, the developed mode, has the most powerful and the ability to apply the test. So in the execution phase, we used two plugins provided by Android Runner, Battery Manager, and the Performers. In the specific test load, for task web GPU test, we ran the test for 5 minutes and break for 2 minutes and repeat it 20 times. It is the same for the Babylon test. So we also ran the test for 5 minutes and break for 2 minutes and repeat it 20 times. It is need to be mentioned that since we used different plugins, so we did the test actually twice. So the first times we used battery manager to measure the battery consumption, and the second one we used the performance to measure the memory consumption and the delayed frame rate. So actually we did it over 80 times, and that's the screenshot when we actually implemented the test.
Hello, this is Iron from Group 5G. In this section, I'll show you the results and data analysis of our experiments. First of all, I'll show you some descriptive statistics of our experiments. We've run two rendering tasks with WebGPU and WebGL. The first task is the WebGPU test, and the second is the Babylon task. And we've recorded these three groups of data: energy consumption, average memory consumption, and delayed frame rate. The box plot of the results is shown on the right side of this slides. As you can see, as for the energy consumption, on the test web GPU test, the two groups of API seem to have the similar performance. And as for the Babylon tasks, WebGL seems to have a lower energy consumption. And as for memory consumption, on the web GPU test, there also seems to be no significant difference. And as for the Babylon task, the WebGL seems to consume more memory. And as for the delayed frame rate, there seems to be no difference between these two API. And this could only be a first impression on the data. And next we'll judge if there is, we'll do tests to see if there is significant difference between the groups of data. And first of all, we'll do a normality test to see if these groups of data conforms to a normal distribution, so that we can choose a proper test to see the difference between the groups of data. And this is an example of the energy consumption on the task web GPU test. As you can see in the table 20, as for the group WebGL, the p-value is lower than 0.05, and for the WebGPU groups, the p-value is more than 0.05, which we can conclude that as for the WebGPU groups, it's possible to conform to a normal distribution, and as for WebGL, it doesn't. So that for these two groups of data, we choose to use the Mann-Whitney test. And this is an example, and all the result of the test is shown here. And only in the groups of delayed frame rate on Babylon text, the two groups of the data conforms to a normal distribution. So we only use t-text for this, and for the other part of our experiment data, we all use a Mann-Whitney test to test if there is significant difference between the two groups. And as you can see, the results only on energy consumption in Babylon text and average memory consumption in Babylon text, there is significant difference between these two groups of APIs, which meets our first impression of the box plot. So we can conclude that in our experiment on Babylon task, WebGL consumes lower energy consumption, and at the same time, it may consume more memory. Okay, that's all. Thank you.
Well, in this section, we delve into the answers to our research questions through the lens of the results derived from our statistical tests and data analysis. In doing so, we also speculate on potential underlying factors that could influence the energy and performance metrics between WebGL and WebGPU. In response to research question 1, what extent does the energy consumption differ between WebGL and WebGPU? when examining the task web GPU test, actually no significant difference in energy consumption between WebGL and WebGPU is discerned. However, the dynamics change when we focus on the Babylon task. WebGPU exhibits a significant evolution in energy consumption, averaging in 49.77% more than WebGL. Given these observations, it can be inferred that the energy efficiency of these technologies might be task-dependent. Web GPU might be more energy-intensive under certain computational loads or rendering interfaces present in the Babylon task. It would be beneficial for developers to consider the specific tasks their applications predominantly undertake before choosing between WebGL and WebGPU from an energy consumption perspective. Regarding research question 2, to what extent does the performance differ between WebGL and WebGPU? Actually, we can see clear differences in performance measures between WebGL and WebGPU. However, these differences depend on the specific metric we're looking at. For the web GPU task, both technologies are on par regarding average memory consumption and delayed frame rate. This suggests that for standard rendering tasks, users and developers might not observe considerable performance benefits switching between these two. However, in the Babylon task, the situation shifts. WebGL consumes on average 66.14% more memory than WebGPU, indicating WebGPU's potential optimizations or memory management techniques that land it on edge in such tasks. Despite these disparities in memory consumption, both technologies seem to deliver comparable delayed frame rates, emphasizing that real performance in terms of frame delivery might not be dramatically impacted by the choice of technology. In summary, both WebGL and WebGPU have their own strengths and weaknesses. Their performance and energy use mainly depend on the specific tasks they are used for. So developers and users should carefully consider the needs of their applications before choosing a technology.
This is how we divide these parts. When we talk about the internal validity of an experiment, we're concerned with the validity of the experimental conclusions. Internal validity can be divided into maturation and validity of measures. Maturation refers to the influence of time on the results. To address this, we randomized the WIP GPU and WIP GL, and also comparated the cooling period between these experiments. The second part is how to use these measurement tools. Our solution for this was to disable other applications during the experiments. Regarding external validity, it considers whether the research can be generalized beyond the specific sample studied. We choose Samsung phones because we believe our findings can be used on other Android devices. Furthermore, we conducted the experiments under a stable Wi-Fi network to ensure the same. We first established our research focused on comparing the two interfaces. The prior research question centered on a comparison of energy consumption, which further broke down into a set of specific metrics. The battery manager we used in our experiments is widely adopted, so there is no need for concern. Conclusion validity refers to the legitimacy of drawing conclusions about the relationship among experimental variables. We address this issue by adopting multiple benchmarks and evaluating the normality of the data. And to counteract these shifts, all experimental procedures were designed carefully, considering them as potential determinants that might influence energy consumption. And for each benchmark, we repeated operation for about 20 times with a fixed time 7 minutes. This approach makes our dataset with great power. That's it. Thank you.